Hello guys. So this is the second lecture of the DSA playlist. There are a total of 7 topics that I will be covering in this lecture, starting with a very basic understanding of a few mathematical tools, and then moving on to very simple common sense based things. From there we'll take it up to time complexity, constraint analysis, and at the end a little about space complexity. That's it. So let's start. The first thing is GP. So we've already done this in in I think 9th and 10th, and then after that I think also in +2 maybe. So a GP, geometric progression, is just a series. Okay. So it follows this pattern. So let's say this is a possible GP. So 1, you multiply 2 into it, you get 2. Then in 2 you multiply 2, get 4. Then again multiply 2, get 8, 16, 32, and it goes on like this. Okay. So in a GP, suppose this is the starting term. Let's call it A. This 2 is called the common ratio. We already know this. I'm not going to stress a lot on it. This is the common ratio. How do you get it? You just take 2 adjacent terms, let's say 16 and then 8, and you divide, and you will get the common ratio as 2. And this is true for any 2 adjacent terms. If this is the case, then sum of a GP, let's say that in this particular series I'm going up to 1024, let's say 1024. So how many terms are there? Let's call it n terms. Total n terms. If this is the case, then sum of this GP is given by this very simple formula: a into r to the power n minus 1 by r minus 1. This is when r is greater than 1. R is the common ratio. A is the first term, whatever it is. And if this common ratio is greater than 1, which it is 2 in this case, then this formula will give you the sum of this geometric progression. Another formula is this one: 1 minus r to the power n by 1 minus r. This is when r is smaller than 1. In most cases, in programming, we will be actually using this one only. Star market, this is important. Cannot forget this. It is like used in a lot of examples, a lot of algorithms. We'll be using this particular formula to get the final time complexity. Next is log. So basics of log, very simple basics. When I write log base a b, this is equivalent to, log base a b is equal to, let's say, c, then this is actually equivalent to writing a to the power c is b. These two things are same. So what does log mean? It basically means to what power should I raise a to get b. So let's say log base 2, 16. To what power should I raise 2 to get 16? So the answer is 4. Why? Because 2 to the power 4 will give me 16, which is this thing exactly. Okay, I will just write it down. Okay. So now this makes it very simple. So if I am having log base 3, 27, then answer is 2. Sorry, 3. Why? Because 3 to the power 3 will be 3 into 3, 9 into 3, 27. So this is just very brief understanding of log. There are a few formulas also. You can just look it up on the internet for log. One important is this: log base a, whatever is here, let's say it is x to the power n, then this is equal to n log base a x. So basically this n in the power will come in the front. Okay, this is important. And also log base a is 1. Why? This is actually very simple. What power should I raise a to get a? 1. Because a to the power 1 will only be a. Okay. And then also log base a1 is equal to 0. Why? Because what power should you raise a to get 1? So anything, if you want, if only because a to the power 0 is 1. We know this. Anything to the power 0 is 1. Okay. Simple log stuff. This is important actually. We'll see why it is important. So we covered this and this. Now the main stuff starts. This is the important part. Let's talk about counting a little. Now we all know counting. So I'm expecting that people will understand this it will not take much time. If I have a series, let's say 1, 2, 3, 4, 5, 6, 7, it goes on up to n. Then question 1, how many terms are there? How many terms are there in this particular series? So let's count. So usually the idea is that forget about n, just find the answer for a smaller problem and then just generalize it. So I will just look at this part. Let's say that the series is only up to 5. Then 1, 2, 3, 4, 5. How many terms? 5 terms. So from 1 to 5 there are 5 terms. So from 1 to n there will be n terms. So the answer is n. How many terms are there? There are total of n terms. Okay. Now the next question is, how many steps? How many steps? Basically, I started from 1 and I have reached n. In each step I am just increasing by 1. Then how many steps did it take to reach n? So if I want to do it for only this much, then the question would be this. I'm starting from 1, going to 5. In each step I'm increasing by 1. Then how many steps did it take to reach 5? So clearly, to count the steps, you need to count in between, like 1 step, 2 step, 3 step, 4 step, and I've reached 5. So if I start from 1 and I reach 5, then it took me 4 steps. Okay, so up to 5, it is taking me 4 steps. Up to 6, it will take me 5 steps. So up to n, it will take me n minus 1 steps. Okay. So this means if I'm starting from 1 and I'm going to n, then there are a total of n terms in this series and it takes n minus 1 steps to reach n. Good. Now let's change it a little. Instead of starting from 1, let's start from 0. Same question. So for question 1, how many terms are there? Clearly there will be 1 extra term because from 1 to n there are n terms. You added 1 0 in the start. So definitely n plus 1 terms are there. And question 2, how many steps? So from 1 to n it is taking n minus 1 step. And because you added 1 extra 0 at the beginning, it will become n minus 1 plus 1, giving us n steps. So n steps are there. So in programming, usually, let's say for arrays or whatever reason, whenever we count, we usually count starting from 0. So this means from 0 to n, there are n plus 1 terms. And from 0 to n, if you are increasing by 1 in each step, it will take you n steps. Okay, 0 to n, n steps. 1 to n, n minus 1 steps. 0 to n, n plus 1 terms. 1 to n, n terms. This is basic counting. Another important series. Let's say I start with 1, then I go to 3, then 5, 7, 9, 11, and I keep going up to some n. In each step, what am I doing? In each step, I am increasing by 2. Correct? In previous example, we were increasing by 1. This was plus 1. In this one, it is plus 2 in each case. So how many terms? How many terms will be there? Question 1. Question 2. How many steps? Okay, notice one pattern. If the number of terms is n, number of steps is just 1 less than that. If the number of number of terms is n plus 1, the number of steps will be just 1 less than that. So this was n plus 1, this became n. This was n, this became n minus 1. So, and you'll understand the logic, like it is very simple. If the number of terms, so if I have 1, 2, 3, 4, 5, 6 terms, the number of steps will definitely be 1 less, always. So 1, 2, 3, 4, 5 steps. Okay, so this is a basic thing. Now, how many terms? Okay, I'm starting from 1, I'm going up to n. In each step, I'm increasing by 2. And the question is, how many terms are there in this series? So again, let's do it for a very small input. Let's do up to here only, up to 9. So I started from 1, I went up to 9. How many terms are there? 1, 2, 3, 4, 5. Okay. So if I think deeply, a little deep in this, then you will see a pattern here. It is basically just last term is 9. So you add 1 to it and then you divide it by 2. So 10 by 2, 5 terms. It is just simple, recognizing the patterns. There is also a mathematical way to do it. 5 terms, because this is actually an AP. 1, 3, 5, 7, 9, 11. It is an AP, arithmetic progression. You can use the formula, the TN formula to find the nth term and all that. And using the logic of AP, you can get the answer. How many terms are there? That is one way. But what I am trying to do is that we want to use minimum amount of maths, okay? We want to focus more on common sense. So common sense says that just go through the series, try to look for patterns. So one pattern that you'll see is, it is always n plus 1 by 2. Like if the last term is n, then n plus 1 by 2. So for 9, it is 9 plus 1 by 2, 5 terms, 1, 2, 3, 4, 5. Let's try for, let's say in somewhere in between you will also have 31, because 31 is also odd. This is basically a series of odd numbers. So up to 31, how many terms will be there? 31 plus 1 by 2, which is 32 by 2, which is 16. 16 terms. So how many terms are there? There are always n plus 1 by 2 terms. N is the last term, so n plus 1 by 2. Okay. And how many steps are there? Just take the number of terms and do a minus 1. So n plus 1 by 2 minus 1. These many steps. You can just, prove it. Let's say we're going up to 9. Up to 9, n will become 9. So 9 plus 1 by 2, there are 5 terms. And you do 5 minus 1, there should be 4 steps. Let's count. 1 step, 2 step, 3 step, 4 step. So total 4 steps. So this works. Another series, an important one, is this one. You start from 1 and you, let's say, multiply 2. Then you multiply 2 again. Oh, I'm sorry. Four into 2, 8 into 2, 16 into 2, 32 into 2, 64 into 2, 128, keep going up to some n. Now, I'm starting from 1, I'm going up to n, and in each step, I'm multiplying by 2. Okay, so in each step, I'm multiplying by 2. Always multiplying by 2. Question is again the same. How many terms? And the second question is how many steps? Okay, so now let's think. How many terms? So now clearly the pattern isn't that simple. But let's try to do it, okay? Let's try to take for up to this. Okay, so now let's do it this way. What we'll do is we will try to think of this series in power of 2, okay? Because clearly we are multiplying 2 in each step, starting from 1, going up to some n in each step, multiplying by 2. And we look at the numbers and we clearly see that these are actually powers of 2 only. So this is 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, 5, 6, 7, and you keep going up to some last term t. Okay. Now let's say I just want to find out from 1 to 16. 1 to 16 is basically this much. So it turns out the last term, which was 16, is written as 2 to the power 4. And how many terms are there? 1, 2, 3, 4, 5. So the pattern is that whatever is the last term, take its power and add 1 to it. So last term is 2 to the power 4. The power is 4 plus 1, 5 terms. So if I get whatever, this n will be written in power of 2. So basically write this n in power of 2, and then whatever is that power, add 1 to it. That will be the number of terms. But how we will do that? The same way we did for these numbers. So we wrote 64 as 2 to the power 6. We wrote 128 as 2 to the power 7. Question is, how did we get here? How did we make this conversion? What we have done basically is just this. 64 is written as 2 to the power log base 2 64. What will be log base 2 64? Log base 2 64, because log base 2 64 will be basically 6. And that is why we write 2 to the power 6. So for n, what can we write? For n, we can write 2 to the power log base 2 n. That's it. This is the last term. This is t basically. Now I have the last term of the entire series, which is this. Take the power. Power is log base 2n. Add 1 to it. This is the number of terms. Okay. So number of terms is log base 2n. Okay, I'll just write it in red. Log base 2n plus 1 term. Okay, and I'll release this one. Okay, so you're writing 64 as 2 to the power log base 2 64, which is 6, so 2 to the power 6. So n will be written as 2 to the power log base 2 n. Okay, so this is the last term. And we saw that for the first 5 terms up to 16, the last term was 2 to the power 4. And the number of terms was just the power of the last term plus 1. Power of the last term was 4 plus 1, 5. Total 5 terms. Similarly, the last term is, for this entire series, is 2 to the power log base 2 n. What is the power of the last term? Log base 2 n. Add 1 to it, that is the number of terms. And what will be the number of steps? So if this is the number of terms, then the number of steps will be just one less, which is log base 2n. Okay, this is one way to do it, and this is just like simple pattern recognizing. Another way to do it, which most people will show you, is through a little bit of maths. So I'm just writing the same series again to sum n. So how do you find the number of terms or the number of steps? Remember that number of steps is way more important than number of terms. Number of terms you will usually have some idea about it, but number of steps, that becomes important when it comes to analysis of the time complexity and all, and I'll show you why. So what you do is, we want to find the number of steps in this particular series. You're starting from 1, we're going up to n, in each step multiplying by 2. How many steps will it take to reach n? That is the question. So the assumption is, let number of steps be k. If there are k steps, okay, then what will be the value of n? So that is again observation. If there are 4 steps, 1, 2, 3, 4, then the value of the last term becomes 2 to the power 4. If there are 6 steps, 1, 2, 3, 4, 5, 6, this is the last one. What is the value? 2 to the power 6. So if there are number of steps are k, then the last term will be what? Last term will be simply 2 to the power k. Okay, so I'm saying that in this entire series, the total number of steps, up to n, this total number of steps is k steps. Then what will be the last value? N will be basically 2 to the power k. So n is equal to 2 to the power k. From here, we can just take log base 2 on both sides. So log base 2 n is equal to log base 2 2 to the power k. As I told you in the previous slide, this form you can always take the power and put it inside on the front basically. So k log base 2 2, and here left hand side will be same. Then again log base 2 n is equal to k, and this is basically 1, as I told you, log base 2 2. So what power should you raise to get to 1? So hence this is 1. This here gives us very important result, which is k is equal to log base 2 n. And what was k? K was the number of steps, which comes out to be log base 2 n. So this is another method to do the same thing, trying to find the number of steps. Now some may find this one easier, some may find this one easier. That is up to you. Doesn't matter which one you follow. But yeah, I can clearly understand that why this one would be preferred, because this is, less of logical reasoning and more of like, maths. So it becomes a patented way to do this kind of, analysis. Okay, so if this is the number of steps, how many terms are there? Number of terms. So as I told you, number of terms is just number of steps plus 1. So number of steps is log base 2n. Just do plus 1. That is the number of terms, and which is the same result as here. Okay, so this was all about counting. Now why is this important? Because in most algorithms, when you do the complexity analysis of time complexity analysis, then you will end up at the end with some series like this. And then you will have to basically find, how many terms are there, how many steps is it taking. Sometimes you will also be required to find the sum, total sum of the series. In that case, if I tell you find the sum of this particular series, then you will clearly understand that this is actually a GP. So you use the Sn is equal to a into r to the power n minus 1 by r minus 1. This formula to get the sum, where r is 2, a is 1. That's it. And n is the total number of terms which you will get after doing this analysis, which is this much. And that is how you get the sum. Okay, so now we are also done with counting. Now let's talk about iterations. So iterations. Let's write a simple loop first. For int I is equal to 1, I less than equal to some n, I plus plus, and inside this loop you are doing some work. Okay, whatever work you're doing, you maybe printing the value of I, maybe you're adding something, you're doing some processing, whatever. But one thing is guaranteed. This is, you're doing some work inside it, but there are no loops. No loops inside this loop, okay? There are no loops inside this loop. Now the question is, first, what is an iteration? Iteration is basically one instance of this loop going through, okay? So how many times will this loop run? It will run for I is equal to 1, then it will run for I is equal to 2, then it will run for I is equal to 3, it will go on and it will run for I is equal to n. So this is one iteration. This is another iteration. Then it runs for I is equal to 3. That is another iteration of this loop. Iteration is basically the running of this loop. The single instance running of the loop is called an iteration. It becomes more clear when you start coding on it. Then it becomes more clear. Okay, let's put something. Let's say like cout I. Okay, I've put some work inside of it. We are doing cout I, let's say. So first iteration is basically whatever is the initial value of I, and the condition, if it is true, it goes inside, it does the work. So that is the first iteration. Then the value of I increases by 1 because it is I plus plus. So when that happens, second iteration begins. So that is what is iteration. Now our motive is to count the number of iterations. Okay, basically that means counting how many times the loop is running. The loop body is running. Okay, so now what we'll do is we'll take different loops of different kind, and then we'll try to figure out how many times the loop body is running. Okay, basically finding the number of iterations for each of those loops. So let's take easy one, which is this one only. Why did I erase it? Int I is equal to 1, I less than equal to some value, let's say 10, I plus plus, cout I. Okay, so this is a simple loop. How many times will it run? 10 times. How do I know? Because first it will run for I is equal to 1. It will basically check this condition. If this condition is true, it will run. So is I less than equal to 10? Yes, it is. So it runs for first time. Then I becomes 2. Again the condition is true. Runs for second time. 3. I is equal to true. Runs for third time, which means the third iteration. Then I becomes 4. True. Runs for the fourth time. And this will keep going up to 10. For 10 also the condition is true. It will run for the 10th time. Then I becomes 11. Condition becomes false. And it will not run anymore. So it runs at the last iteration is the 10th iteration. So this means it runs 10 times. Now the question is, if I replace this 10 by some n, how many times the loop will run? It will run n times. Okay, so a simple loop that is starting from 1 going up to n. What is the value of I? I is starting from 1 going up to n, in each step increasing by 1. So 1, 2, 3, 4, dot dot dot. Now we have already seen these. We have already seen this pattern. And this pattern, how many terms are there in this pattern? There are n terms. Hence this loop is running n times. So there are two ways to do it. One, follow the loop, trace it, count how many times it is basically doing the work, get some idea on, what will be the final result. Or try to understand the pattern that the loop variable is following. So what is the loop variable? If you have gone through basics of C, C++ or whichever language that you are following, then you will know that there is always some variable that is governing the loop. So this loop is governed by the variable I. So find what pattern is I following. I is following this pattern. So just count the number of terms in this pattern, n terms, hence the loop will run n times. That is it. Okay, now let's do it for this loop. I is equal to 0, I less than equal to n, I plus plus, same thing, see out I. How many times will this loop run? What is the number of iterations? Okay, so let's try to find it out. I is starting from 0, going up to n. At each step, we are increasing it just by 1. So I is starting from 0, increasing by 1, and then at the end it is reaching some n. So we have already seen this particular pattern. How many terms are there? N plus 1 terms. Hence, the number of iterations or the number of times the loop body will run is n plus 1. Now, what if this equal to sign was not here? Had this equal to sign not been here, then what will happen? It will start from 0. It will start from 0, increase each time by 1, but now it will not go up to n. It will go up to n minus 1. Now how many terms are there in this series? If you use your head, then you will understand there are n terms. Okay? Why n? Because again, do it for a smaller section. From 0 to 4, how many terms are there? Last term is 4 plus 1. 5 terms are there. So for this entire series, last term n minus 1. Do a plus 1, n terms will be there. Okay? So from 1 to n, there are n terms. From 0 to n, there are n minus 1 terms. N plus 1 terms. From 0 to n minus 1, there are n terms. From 1 to n minus 1, there will be n minus 1 terms. In each of these cases, we are increasing by 1. So we are doing basically I plus plus. So in this case, the answer would be n terms. So n times the loop will run. Another way to go through this is basically just counting. I is going from 0, I less than n is the case, and each time you're doing I plus plus, so basically making I increase by 1. So for I is equal to 0, is I less than equal to n? Yes, it is. So true. So loop runs, so I'll just write number of iteration 1. Then I becomes 1, is I less than equal to n. Let's say n value is 10, or let's say n value is 5. Okay, so I less than n, yes, true. So loop will run second time. So same for 2, 3, it will be true. Loop will run for third time, fourth time. Then I becomes 4. I less than n value is 5. Is this true? Yes, it is true. So the loop runs for the 5th time. Then I value becomes 5. Is 5 less than 5? Is this true? No, it isn't. This is false. So loop will not run any further, and loop has run 5 times. Okay, which is basically n times. And that is why this was n. So follow any one method. It is up to you. Both will work in any case. Let's take another example. So what you can do is, every time I write the loop, pause the video, try to figure it out, like how many times, what will be the number of iterations, how many times will it be running. Okay, let's do it for this one. For I is equal to 1, I less than equal to n, I is equal to I plus 2. Pause the video, try to figure it out. How many times will the loop run? So now if I look at it, I'll follow the same method. I is starting from 1, going up to some n, each time increasing by 2. So I increase it by 2, increase it by 2, increase it by 2, increase it by 2, keep doing it up to you reach n. So we've already seen this. We've already seen this pattern, right? It was this one. How many terms? N plus 1 by 2 terms. So this will be again n plus 1 by 2. N plus 1 by 2 times the loop will run. I can prove it. To prove it, I will just trace it. I value 1, I less than equal to n, and let's say n is 9. So for 9, by this formula, it should be 9 plus 1 by 2, 5 times the loop should run. Okay. So I is equal to 1. Is I less than equal to 9? Yes, true. Loop runs. Then I becomes 2. Is 2 less than equal to, I becomes 3 because it is I plus 2, right? So 1 plus 2 is 3. Is 3 less than equal to 9? True. Loop runs. Then again plus 2. I becomes 5. Is 5 less than equal to 9? True. Loop runs. Then again plus 2. 7. Is again 7 less than equal to 9? Yes. True. Loop runs. Then again plus 2. 9. Is 9 less than equal to 9? True. So loop runs. And again plus 2. 11. Is 11 less than equal to 9? No, it isn't. False. Loop will not run. So how many times did the loop run? The loop basically ran 1, 2, 3, 4, 5 times, which is this one. Same thing. This method, we are basically just trying to understand what the loop is doing, and based on that we are trying to figure out the complexity, the number of iterations. And here we are basically just tracing the loop and trying to figure out how many times the loop ran. Both should give the right result. Okay, so this example is done. Now, let's move to the next. Now, it isn't necessary that you will always have increasing loops. You can also have decreasing loops, right? So let's say something like int I is equal to, let's say 10, I greater than equal to 1, I is equal to I minus 2. If this is the loop, how many times will this loop run? See out I. So again, you see, you just try to understand what the loop is doing. Okay, so the loop, inside the loop you're just printing stuff, but how many times? So I starts from 10. Each step it is decreasing by 2. So this becomes 8, then becomes 6, then becomes 4, up to 1. Okay, so 2 and 2 minus 2 will be 0. It won't be 1. Okay, so after 2 it will become 0. It will never reach actually 1. It will from straight away from 2 it will go to 0 and the loop will end. So the question here is, for which values of I will the loop run? It will run for 10, it will run for 8 because 8 is greater than equal to 1. For 6 also it will run. For 4 also it will run. For 2 also it will run because 2 is greater than equal to 1. Then you will do minus 2. I will become 0, and then the condition is false. So it will not run for this loop. How many times is the loop running? It is running 5 times. which is basically just the start value by 2. So if this, instead of 10 this was n, so this loop will run n by 2 times. So you see, what I'm trying to do is, I'm trying to get this thing in your head that it is not necessary to always trace your loops, because when you start writing complex algorithms, the loops will also become complex and it will become difficult to trace all of those. Okay, it will be time consuming. You don't have that much time in your coding interviews or in your online assessments or lead code contests or whatever. You don't have that much time that you'll go on tracing each loop to the end and then figure out what is the number of times the loop is running. No. The idea is always try to somehow figure out what is this loop actually doing. Okay, that will give you the idea of how many times it will run. So this loop, it is basically just printing, starting from a particular value, it is printing the the even numbers in a decreasing manner. Okay, so what is the last even number that it will print? It will print 2, because after that it will not be printing anything, because 2 is the last even number in this series. Okay, now let's have this one. Now we are increasing the complexity a little. Okay, so now we have a loop inside of a loop. Till now, whatever examples we saw, there was no loop inside the outer loop. Okay, or let's make this m, let's keep this n, and inside this I'm doing cout whatever, let's say I and also j, both. Okay, now how many times will this entire thing run? So the idea is, okay, tell me one thing. For the first value of I is equal to 1, the condition is true, it goes inside and it runs this entire loop. Okay, this runs completely from j is equal to 1 to j is equal to n. It will run and this loop will be done, and after that I plus plus will happen and I will become 2. What does this tell us? This tells us that for each value of I, the j loop runs entirely. Okay, so for I is equal to 1, j will go from 1 to n. Then for I is equal to 2, j will go for 1 to n. For I is equal to 3, j will go from 1 to n, and it will keep going. For I is equal to m, j will go from 1 to n, and that is the end of the entire loop. Okay, so to find out, okay, when we are trying to find out how many times the loop is running, and there are multiple nested loops like these, then basically what we are trying to find is, we are trying to find how many times the innermost part is running. So this is the innermost part. How many times will this part run? So clearly it will run n times, because this is a simple loop. This inner loop, if I just look at it, this is a very simple loop, 1 to n. Okay, so this loop runs n times. Okay, but it will run n times for I is equal to 1, n times. Then it will run n times for I is equal to 2. Then again this part will run n times for I is equal to 3, and it will go down up to I is equal to m. So n times for I is equal to 1 plus n times for I is equal to 2 plus n times for I is equal to 3. Keep doing this. Last also n times for I is equal to m. So how many n's are there in this series? N plus n plus n plus n. I'm basically just adding n. How many times? M times. M for mango. M terms are there here. Why m terms are there? Because I is equal to 1 to I is equal to m. From 1 to m, each time increasing by 1 only. So it is basically there are m terms. So this comes out to be m into n. So this entire, the innermost part will be running m into n times. Now let's trace it. Okay. I'm just rewriting it. Should have just copied it from there. Okay. N j plus plus plus, then C out I j. Okay. What will happen first? First, this instruction will run, I becomes 1. Is the condition true? Yes, the condition is true. It will go inside, then j is equal to 1. Is the condition true? Yes. J plus plus C out ij. It will do its work. Then j will become 2. J will become 3. It will keep going. This loop will keep running. Okay. Up to j becomes n. When j becomes n, this loop is done. Okay. After that, I plus plus. So I becomes 2. Now when I becomes 2, again, j is equal to 1, j less than equal to n, j plus plus. So this entire thing will happen again. Then I plus plus. I becomes 3. 1, 2, 3, 4, dot, 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 n. It will keep going like that. Okay. Up to, at the end, I will become m. And again, this will run from 1 to n. So, n times plus n times plus n times plus n times, last also n time. How many times? M times. M times this n is happening. For m number of times, the inner loop is running n times each. Okay, so for I is equal to 1, it is running n times. For I is equal to 2, it is running n times. So, n plus n plus n, dot 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 plus n. How many times? M times. Hence, this total thing is m into n. Same thing. Okay. These are the most common loops. We will see 2 more. Okay, 2 more. Okay, let's see this one. This is an interesting one. For I is equal to 1, I less than equal to 5, I plus plus. For j is equal to I, j less than equal to 5, j plus plus. C out ij. Question is same. Find out how many times, the innermost part will run. Okay. So let's figure it out. Idea is same again. Idea is completely same. For each value of I, this inner loop will run. But the thing is that inner loop is dependent on the outer loop because inner loop starts from I. So when this happens, it is better to trace it. It is better to trace it because now making assumptions becomes difficult. Okay. So what I am going to do is, what you do is just think for I. For I is equal to 1, j loop runs. J loop will run from 1 to 5. For I is equal to 2, j loop will run from 2 to 5 because j is equal to I, j less than equal to 5, j plus plus. Then I is equal to 3, this runs from 3 to 5. I is equal to 4, this runs from 4 to 5. I is equal to 5, this runs from 5 to 5. And then this is done because I less than equal to 5 only. Okay. So from here, can I clearly say that if I try to calculate total work for the first iteration of outer loop, 5 times the innermost part is this part is running. For I is equal to 2, it is running 4 times. I is equal to 3, 3 times. I is equal to 4, 2 times. I is equal to 5, 1 time. So total is 5 plus 4 plus 3 plus 2 plus 1, which is basically this. Now tell me if you have seen this series before, this sum. This is basically 5 into first 5 terms is 5 into 5 plus 1 by 2. So 5 into 6 by 2. This is 15. 15 times this inner loop will run. Okay, and what will it print? Think about it. What will it print? For I is equal to 1, the inner loop runs for I is equal to 1, j goes 1 to 5. So when you print this, I1 and j is equal to 1, this will print 1, 1. Then j becomes 2. It will print 1, 2 because I is fixed at 1. For this 1 to 5, I is 1, but j is going from 1 to 5. Then j becomes 3, so 1, 3. J becomes 4, so 1, 4. J becomes 5, so 1, 5. Then what happens? Then I plus plus happens. I becomes 2. And for I is equal to 2, j will run from j is equal to 2 to j is equal to 5. Like this. And in each time, you're printing cout ij. So 2, 2, 2, 3, 2, 4, 2, 5. For I is equal to 3, it will be 3, 3, 3, 4, 3, 5. For I is equal to 4, 4, 4, 4, 5. For I is equal to 5, only 5, 5. And then it is done. Okay. Now I've written here the number of times the innermost part will run. Now the question is, what I do is, instead of 5, let's make it n. Okay, here also n. Now what happens? If this is n, then the total number of times will be just this n into n plus 1 by 2, because this is what it was, right? For when it was 5, our answer was 5 into 5 plus 1 by 2. When it is n, our answer will be n into n plus 1 by 2. That's it. And what will happen? For I is equal to 1, it will run from 1 to n. For I is equal to 2, it will run from 2 to n. For I is equal to 3, it will run from 3 to n, 4 to n, 5 to n, 6 to n. At the end, this will reach n when it will run, and then the inner loop will run from n to n, which is basically just once. Okay, so this way, this particular loop will proceed. Now this is also important. Okay. Let's see another loop. This one's actually pretty easy. I is equal to 1, I into I less than equal to n, I plus plus. How many times will this loop run? I'm doing some work inside of it, okay? How many times will this loop run? I is equal to 1, I square is less than equal to n, I plus plus. If you've seen the previous video, the video in the playlist before this one, lecture 1, then you will know how many times this loop will run. Basically, this part, can I write it like this? Can I write it like this? Right, so this loop is basically just this. I is equal to 1, I less than equal to root n, I plus plus. So my I is starting from 1, going up to root n, each time increasing by 1. So how many terms will be there? Simple, root n terms. So this inner part of the loop will run root n times. That's it. Moving to the next. I is equal to 1, I less than equal to n, and this time I is equal to I multiplied by 2. Multiplied. Cout I. Now what will happen in this case? So again, we'll do the same thing. Starting from 1, we're going up to some n. Each time we're multiplying by 2. So 1, 2, 2 into 2, 4, 4 into 2, 8, 8 into 2, 16, 16 into 2, 32, 64, 128, dot 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 up to some n. Question is, how many times will this loop run? So I is going from here to here. how many times the loop run, basically how many terms are there. So how many terms are there? We've already seen this. There are log base 2 n terms, n plus 1, sorry. Log base 2 n plus 1 terms are there. So the loop will run log base 2 n plus 1 times. Let's prove it. Let's trace and prove it. So I is equal to 1. Sorry. I is equal to 1. I less than equal to n. Yes. So the loop will run first time. I'll just count the ticks. Or let's say for this case n is equal to 16. Okay. Otherwise we will just keep on doing and it won't end. So n is equal to 16. So by this formula, this should run log base 2 16 plus 1. Okay, 16 is 2 to the power 4, so 5 times. Okay, let's see. I is equal to 1, true, the loop runs. Then I becomes 2. Is I less than equal to n? True, loop runs. I becomes 4 because each step you have to multiply by 2. So true, loop runs. Then 4 into 2, 8. Is 8 less than equal to 16? Yes, true, loop runs. Then 8 into 2 is 16. Is 16 less than equal to 16? Yes, true, loop runs. Then 32. Is 32 less than equal to 16? No, so false. So loop will not run. How many times is the loop running? 5 times. So this is correct. Okay. So why am I showing you these loops? Because now what I'll do is I will tell you 2 important things, and after that I'll just give 3-4 random loops and you have to guess. And it will actually become very, very easy. Okay, so till now, let's do a quick revision. Simple loop, I++ is happening and you're going from 1 to n. Then there are the n times the loop is running. Good. Okay, if it is starting from 0, then it will be n plus 1 times. That is okay. Okay, if it is doing I plus 2, then you're basically jumping half the numbers, hence n plus 1 by 2 times the loop will run. Now what will happen if it is I plus 3? If it is I plus 3, then it will become n plus 1 by 3. Okay, you just change the denominator. Then I is equal to I minus 2. Again same, n by 2 terms. Okay, also you don't actually have to worry about these small sorry. Also, actually, you don't have to worry about these small constants, these plus 1, or in this case, where is the log 1? Log 1 also here there is a plus 1. If you even forget that, that is okay because of the next thing that I'm going to tell you. Okay, let's start. Number 1, addition. Addition rule, which basically says that there is a program, okay, and it has 2 loops like this. There is a for loop, okay, that runs n times. Then there is some work. Then again there is a for loop that runs m times. Then total complexity of this program, total if I ask you how many times the executions are happening or how many times the loop running is there, you will just say n plus m. Why? Because n iterations for this loop, m iterations for this loop. So total number of iterations, n plus m. Addition rule. And multiplication. Multiplication rule is this. Very simple again. If there is a for loop and inside there is another for loop, okay, if the inner loop runs n times, outer loop runs m times, then total number of iterations is n into m. We have already seen this, okay, but we can extend it, okay, we can again extend it. So there is a for loop, inside that there is again a for loop, inside that there is also a for loop. Okay, now there are 3 nested for loops. Innermost runs n times, middle one runs m times, outermost runs o times. Then total number of iterations is n into m into o. Okay,
So you keep multiplying. If it is nested one inside another, you multiply the number of iterations. If it is outside, one after the other, you add the number of iterations. Now we are moving to the big O notation. Time complexity and big O notation. Basically, why we are learning this, calculating the number of iterations and all, is because we want an estimation to know, like, okay, I'll explain it this way. You have two algorithms, algo 1, algo 2. Okay, there are these two algorithms, both solve the same problem. Okay, both of these solve the same problem. Let's say the problem is count number of factors of a number, factor of n. This is a question that I solved in the last video, the lecture 1. So count number of factors of n. So the first algo does the simple, check every number from 1 to n, which is the first algo. So that particular will take, for any n, it will take n iterations. And there is another algo 2, which will be going from 1 to root n, so that takes root n iterations. Now, okay, also people who haven't seen that video, it is completely okay. Okay, you don't have to understand. In fact, okay, let's remove this. Just understand this, that there are two algos, algo 1 and algo 2. First both of these solve the same problem. Okay, they are the solution, they are the algorithms to solve the same problem. Both of them are giving me the result, but the first algo is taking n iterations while the second algo is taking root n iterations. Okay, then clearly this algorithm will take more time. Why will it take more time? Because it has more work to do. Suppose n value is 10 to the power 18, then this has to do 10 to the power 18 iterations, while this only has to do 10 to the power 9 iterations. Since it has to do lesser iterations, it will take less time. Hence, I can say this algorithm is overall faster. So preferably, I should be taking this algorithm to solve the problem, not algo 1. Why? Because it is slower, right? It is doing more work. To solve the same problem, I have two algorithms. First algorithm is taking more time because it has to do more work. It has to go through more iterations. But the second algorithm is taking less time. It is faster. Why? Because it is taking less time, because it is doing less work. Only root n iterations. Hence, algo 2 is preferable. So, time complexity, big O notation, big theta notation, or omega notation, all of these things help us basically decide which algorithm to take. All of these, big O notation, there is also omega notation, theta notation. All of these are basically mathematical tools that let us decide which algorithm should I take. Okay, so let's see how to write big O notation. So also there is a lot of theory behind big O notation, and there is also omega notation, theta notation. All that is covered inside as a syllabus of GATE, MTech entrance exam GATE. It is not part of the DSA playlist because it is not actually required. While solving problems or in interviews and all, big O is the most important thing. It is what is important. Okay, so that is why we're focusing on this only. We're not focusing on the theoretical aspects because those are never asked. Very it will only be asked in interviews for MTech entrance, PhD entrance, all those things. So if you're learning just DSA, it is not relevant. Hence, I'm going to start with big O. So steps are easy. Calculate number of iterations. That is why I taught you how to calculate the iterations. Second, remove smaller terms, or you can say lower order terms. Third, remove leading constants. And what is left is your answer, is the big O notation. So for that, put answer inside this thing. Okay. Now let's do it for all the operation, all the loops that we have seen. Okay, let's do this one. What is the time, when people ask you what is the time complexity, they're basically, I'll explain what is exactly time complexity. If you want to know the theoretical aspect behind it, I will ask you, but this is how they basically write down the time complexity. So in some questions, usually in MCQs and all, they will give you direct, this is a particular loop, this is what is the time complexity of this loop. So time complexity for this one is what is the number of iterations? Number of iteration is n. Okay. There are no lower order terms, there are no constants, leading constants, so just put inside O, and this is the time complexity, big O of n. Second, this one, what is the number of iterations? N plus 1. Remove any lower order term. So what is the lower order term? 1 is the lower order term. Remove this. What is left? N. Put this inside this, big O of n. That is the time complexity. You see, that is why I said don't worry about this plus 1 and all. It does not matter. Only the highest order term matters. Next, this loop. Okay, what is the number of iterations? Okay, I've made it I is, let's stick to I plus 2. Okay, number of terms, number of iterations was n plus 1 by 2. Okay, this can be written as n by 2 plus 1 by 2. Remove lower order term, you're left with n by 2. Remove leading constant, because this is actually half into n. So remove the leading constant, you are left with n. So big O of n is your answer. This is your time complexity. For this loop, n by 2 is the number of iterations. Remove the constant, leading constant, you're left with n. Big O of n is the answer. For this loop, number of iterations is m into n. Okay, so is there any lower order term? No. Are there any constants? No. M and n both are involved, both are variables. None of these are constants. So put this inside the loop, inside the big O notation. This is called the big O notation. Okay, so big O of m into n. Okay, had this m, instead of m, if this was n, then this will become big O of n square. Okay, because it will become n into n, so big O of n square. This loop, okay, this is the same loop. This loop, okay, this one, total number of iterations was this, n into n plus 1 by 2. So first thing that you do is, you write it like this, n square plus 1 by 2, which can be written as n square by 2 plus 1 by 2. Remove the lower order term, remove the constant. So answer is big O of n square. Next, this loop, how many times is it running? Root n times. There are no lower order terms or constants, so the complexity is big O of root n. Then this one, total number of iterations is log base to n plus 1. Remove lower order term and remove the constant, means remove this 2 also, because this is also a constant. Remove this, you're left with big O of log n. So again, that is why I told you this plus 1 does not matter, this base and all. You don't actually have to remember all this. Approximations, okay? Complexity analysis is all about approximations. You don't have to be exactly correct. Just approximate it correctly. So big O of log n is the complexity for this particular loop. Now, I will write a few loops. Suppose this is some program. Inside this, I'm doing O1 work, big O of 1 work. Now, what is this big O of 1? You've already seen big O of n, big O of n square. What is this big O of 1? So big O of 1 basically means that whatever is inside this is not dependent on any n. Okay, something, there are no loops inside of this. There is nothing that is dependent on n. There will be some printing statement, maybe C out I, or maybe there is some addition that we are doing, s is equal to s plus I, something like that we are doing, but it is not dependent on n. So after that I have j is equal to 1, j less than equal to n, j plus plus. Inside that I have for k is equal to 1, k less than equal to n, k plus plus. Okay, and inside this I've done O1 work. First I'll give an example of O1 also. Wait, then we'll go back to that one. So for I is equal to 1, I less than equal to 10, I plus plus. How many times will this loop run? See out I. This loop will run 10 times. Okay, so what will be the big O notation? Big O of 10. But as I told you, we don't consider constants, right? This is a constant. So instead of writing 10, you will just, remove this and write 1. Big O of 1. Why? Because this loop always runs 10 times. It is not dependent on any input, any n, m. There are no variables here. It is independent. It always runs 10 times. So this means in a particular computer, if one instruction is taking 1 second, then this program will always take 10 seconds, no matter what. On that machine, this program is always going to take 10 seconds. Okay, but if I have I is equal to 1, I less than equal to n, I plus plus. Okay, see out I. Now this, what is the complexity of this particular loop? It is big O of n. Okay, n times the loop runs. There are no constants or lower order terms. So big O of n is the complexity. Now, on the same machine, I'm running this loop. One instruction takes 1 second. Okay, n instructions will take n seconds. I'm considering that the loop, there are 10 instructions in this loop. I'm considering in this loop there will be n instructions. It will take n seconds. That is why it is big O of n, because it is dependent on n. If n increases, if n is 10 to the power 18, then it is going to take 10 to the power 18 seconds. If 10 to the power 100, then it will take 10 to the power 100 seconds. But this one is independent. It always takes 10 seconds. That is why this one will be written as big O of 1, while this one will be written as big O of n. Going back, what will be the complexity of this one? Let's see. First is this loop, which I is equal to 1, I less than equal to n, I plus plus. So clearly the loop runs n times, and each time it is doing big O of 1 work, which is equal to big O of n. Consider this just as, mathematical one while doing the calculations. So this loop complexity is big O of n. This loop is a nested loop. Inner loop runs from k is equal to 1 to k less than equal to n, k plus plus, simple loop. So basically inner loop is running n times. Outer loop also similar, j is equal to 1, j less than equal to n, j plus plus. So outer loop is also running n times. So as I told you, multiplication rule, n into n. This entire thing is running big O of n square times. And total complexity will be big O of n plus big O of n square. Now again, ignore the lower order term. You are left with big O of n square. That is the total complexity of this particular program. Okay, simple. Now that you have in your mind different patterns, you already know, okay, this one will take n time only, because inside it you're doing some constant work or one work, and the loop runs n times. So n time. This is clearly a n square, because outer loop n times, inner loop also n times. So n square. But had this been k is equal to I, k less than equal to n, then you will have to calculate for this one, which will in big O notation will again come out to be this only. We have already done this here. Yeah, this one. In big O notation, it comes out to be n square only. Okay. Okay, coming now to the next topic. Now if I go back to the list, the main list, okay, where is it? We're done with number of iterations. We're done with big O notation. Next is constraint analysis.
n space complexity. Okay. Okay, so let's do constraint analysis now. So what this means is every question that you solve in DSA will come with some constraint. I'll show you. If we go to lead code and let's check, okay, let's see the current problem. Like this is the lead code's daily challenge. So today's challenge. So you see, there is this question, there are examples, and then there are constraints. You see, s.length cannot be more than 10 to the power 5. Now this information is crucial because this will decide what complexity solution should I write. Should I write n square solution? Will it work or will it give me some error? Should I write n time solution? Should I write root n solution? Should I write log n time solution? What kind of solution is okay according to this constraint? Based on this constraint only, the online judge, so when you click your run or submit button, the online judge is checking your solution against multiple test cases. Those test cases are hidden. Okay, they are hidden to you, but one thing that is guaranteed is that all of those test cases will actually basically follow these two constraints. So major one is this one, that s.length is less than or equal to 10 to the power 5. Basically it is same as if saying this, n is less than or equal to 10 to the power 5. Now if n is less than or equal to 10 to the power 5 and I write n square solution, then for the maximum value of n, which is 10 to the power 5, it becomes 10 to the power 10. And if I go with this solution, this will not work. It will give me an error called time limit exceeded, TLE. But if I write an ON solution, then for the maximum n, it will be only 10 to the power 5, and this will work. So how to decide which one will work, which won't work? Basically the logic is this. The online judges that are basically testing your code against different test cases, how they work is they are capped, mostly are capped at 1 gigahertz. Okay, this basically means that 10 to the power 9 instructions per second. So they can execute 10 to the power 9 instructions per second. So the logic is you will have to write your code in such a way that your overall number of instructions does not exceed 10 to the power 9. So if you have, it basically depends on your constraint. So if constraint is that n is less than or equal to 10 to the power 9, then it is then only big of n solution will work, because big of n solution will give you for max value of n 10 to the power 9. So this works because 10 to the power 9 is okay. If you write n square solution, then for maximum value of n, this becomes 10 to the power 9 into 10 to the power 9, which is 10 to the power 18. This won't work. This will give you TLE. Why? Because it can do only 10 to the power 9 instructions per second, not 10 to the power 18. Okay, if you go for n log n, then this is for max value of n, it is 10 to the power 9 multiplied by log n, which is 9, which is again more. So this one, but it is not too much, right? It is more. It is 9 into 10 to the power 9, which is more than 10 to the power 9, but it is not too much. So here it is ambiguous. You cannot, foretell that, okay, will it give me TLE or not? You'll have to run it and check whether it is giving TLE or not. This one is ambiguous. But if the constraint is less than or equal to 10 to the power 5, then a big of n square solution will not work, because n square means 10 to the power 10, which is more than 10 to the power 9, it will not work. But big of n solution will work, because that would mean 10 to the power 5, okay. Big of n log n will also work, because n log n will be what? 10 to the power 5 n multiplied by log n. So log n will be 5. When we are saying log n, we are basically taking log base 10n. Okay. So this will also work because it is less than 10 to the power 9. Okay, let's go for root n solution. A root n solution will be for maximum value of n, it will be like 10 to the power between 2 and 10 to the power 3. So it will work with 2 point something. This will also work. So what I'm trying to say is, based on your constraint, you have to foretell whether the solution that you are thinking will work or not, because otherwise you will be wasting time. Okay, how we do is, we read question, then we think, we get the solution, then we submit, then let's say the solution, the complexity was too much, you get a TLE, and then you think again for a better solution which will not give you TLE. But a way better approach would be, after thinking, check complexity and constraints. Based on that, if it is feasible, like suppose you came up with a solution which is an n square solution, then you saw the constraint and you were like, okay, this is total will be 10 to the power 10, this is not going to work, then you will not go to solution, you will go back to thinking, and then you come up with a, let's say, n solution, n time solution. Then you are like, okay, 10 to the power 5, this is less than 10 to the power 9, so yes, this will work. And then you start your coding and then submit, and you will avoid this TLE. You will get AC accepted. Okay, so this is just a tip. Again, this is something that you will get the hang of after doing, let's say, first your 20-30 DSA problems. Okay, after that only. But this is the trick. The trick is that make sure that your total, just whatever is your complexity, whatever is the constraint, based on that, find the maximum number of instructions and check if it is less than equal to 10 to the power 9 or not. Remember that this thing, if it is 10 to the power 7, 10 to the power 8, it will work. But 10 to the power 9 or close to 10 to the power 9, it becomes ambiguous because you never know. This is all approximation, right? So maybe the online judge in which you are submitting, maybe lead code will accept, but code forces will not accept. That may happen. But for 10 to the power 7, 10 to the power 6, lead code will also accept, code chef, code forces, any platform will accept. Okay. But as your number of instructions get closer to 10 to the power 9, it becomes more and more ambiguous. In that case, you will have to write down the solution and test it. Okay. That is it for constraints also. Now the easiest is space complexity. Space complexity. So this is very simple. Let's say you write a program. Okay. For int I is equal to 1, I less than equal to n, I plus plus, and then you're basically adding. Okay. So this is not JavaScript. Int s is equal to 0, s is equal to s plus I. Okay, this is a simple program. I ask you, what is the complexity? Time complexity. So what is the time complexity? A simple one loop. Inside this is constant work, this is inside constant work. The loop runs n times. So this is constant and this is big of n. So constant plus big of n will give you big of n. So total time complexity is big of n. What is the space complexity? So space complexity is just the amount of extra space that you are using. Okay. Extra space. When I say extra space, this means space apart from input and output. Okay. So what is the extra space that we are using in this program? We are using this variable. Then there is this variable I, and that's it. There are only two variables that we are using. Okay, and both of these variables are not dependent on n. Hence, why is it not dependent? Let's say int is like 4 bytes, right? Integer is 4 bytes. So we have this one 4 bytes and then this one 4 bytes. So total 8 bytes.
That's it. Total 8 bytes of storage. No matter what is the value of n, it will always be 8 bytes only. It is not going to change. So this one, we will say it is constant extra space because it is not dependent on any variable. But if I have a program like this, there is an array A, int A of size n is equal to blah blah blah. Let's say this is coming from user only. Int A size maximum 1000. If you have C and C++, then you will know that you have to put some size here. Okay. And then there is int n. You see in the value of n. Then you for I is equal to 0, I less than equal to I less than n, I plus plus, you do C in A of I. After that, when this is done, you are let's say only this much. We are doing only this much. So what is the time complexity? Time complexity, again, this is just a declaration. Constant work. This is again constant work. This is again constant work. Inside the loop, constant work. How many times will this loop run? It is starting from 0 going up to n minus 1. We've already seen this. This is running n times. So this loop is entirely big of n. So O1, 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 On. Complexity is On. Okay. Space complexity. Space complexity, let's see. This is one variable, n, 4 bytes. This is one variable, again 4 bytes. This is this array of size 1000. Okay, and it is of type integer. So 1000 integers. It is an array of integers. So basically this is the array. There are 1000 integers in this array. So this becomes 1000 times 4, 4000 bytes. But out of this, okay, yeah, this will be 4008. Actually, out of these 1000 integers, only n are being actually used, but we are allocating 1000 integers in memory. So it will take 4008 bytes again, which is a constant. It is not dependent on any n. So this is big of 1. But now what we do is, in the next example, let's say we declare a vector int a. Okay, and for int I is equal to 0, I less than n, I plus plus, a dot push back I. Now what is a vector? Vector is just an array, but you don't have to provide the size beforehand. Okay, it is an array. For right now, just know this, that it is an array only, but you don't have to provide any size. Okay, so initially it has nothing. Then you start pushing into it. First 0 is pushed, so 0. Then I becomes 1, 1 is pushed. Then 2 is pushed, 3 is pushed. This way, total n, 0 to n minus 1, 0 to n minus 1 will be pushed inside this array. So what is the time complexity? This is again O1, this is again O1, this loop is again big of n. Okay, so time complexity is same, big of n. But what is the space complexity? Space complexity, this time, this is 4 bytes plus this is 4 bytes plus this vector. Now you see, vector size is not provided beforehand. This means that vector size is dependent on n, because the number of items that we push inside this array will become the size. So we are pushing from 0 to n minus 1, total n numbers. So the size of this array at the end is dependent on n, which is basically n multiplied by 4 bytes, because it is an integer array, integer vector. So n times 4 bytes. So now it is dependent on n. So apply the same logic. Big O of 4 plus n times 4. Remove lower order, remove constant. So big O of n. So space complexity is big O of n. That's it. Okay. Just remember one thing. Sometimes in questions, you will be provided with input. Like here we are creating this array. Hence it is part of your space complexity. But if this array is already provided to you, then you will not include it. Okay. Because input and output is not part of space complexity. Okay, whenever they say extra space, auxiliary space, space complexity, don't include input and output. I'll give you an example. A very simple example would be this question that was in yesterday's challenge.
Morning.
This was yesterday's April 5th lead code challenge. So this lead code challenge, this is written in JavaScript, but it is the same thing. Okay, you don't have to worry. I'll just increase the font size here. This is the code that I wrote. This is basically a function. You don't have to understand the code, but just understand this. This S was already given. Okay, when I write the space complexity of this program, S was already given. S is an array. S is already given. I don't have to worry about the size of S. Okay, it is already given, so don't include it. What will be the space complexity? I have declared this array extra. Now this extra array that I have declared, this will be counted as my space complexity. Okay, so if I just okay now. Okay, so what will be the time complexity of this little code? This is O1. This is again some declaration O1. This is a loop, simple loop that is going from 0 to s dot length. Let's say s dot length value is n. Okay, I will call s dot length as n. So this loop runs n times. Okay, inside it we are doing simple constant work. This is some comparison constant. This is again some if else constant. And this is some pushing inside the array. This is also constant. And at the end this line is also constant. So inside this loop we are only doing constant work. So total complexity, time complexity will be big O of n plus O1, O1, O1. So we will ignore all that and answer is big O of n only. What is the space complexity? Let's think about the space complexity now for this one. So space complexity, see, what are the different variables that I have here? I have S, I have this answer, I have this I have this top, and that's it. Okay, S is provided by the question. Okay, this is the input, so don't consider S. Answer, I have declared answer. This has been done by us, so consider this. This is an array and you don't have to understand the code here, but this array, the maximum size that it will take is n. Okay, so big O of n for this array. Then there is this I. So you're creating one variable I and changing, so that is just 4 bytes. This is the stop. I'm creating this stop, but you see this stop is created n times, but only once. Like for example, for I is equal to 0, top is created. Okay, top is created and you'll do some work with it and then it is destroyed. Then for I is equal to 1, a new top is created. Then this is also destroyed. Then I is equal to 2, a new top is created. And then this is also destroyed. So whatever variables that you are making inside the loop, don't count those because they don't exist throughout the program. Okay, they exist in that iteration only. This top exists only for I is equal to 0. Okay, one common misconception is for I is equal to 0, top is created. Then for I is equal to 1 also top is created. Then I is equal to 2, top is also created. And this way there will be total n tops. But that is completely wrong. There will never be n number of top. Okay, there will be at a time there will be only one top, because for I is equal to 0, top is created, but then I plus plus happens, iteration changes and this top gets destroyed. When iteration changes to 1, new top is created, and then when this iteration is done, this top is destroyed. Then for I is equal to 2, a top is created, then iteration changes, this top is also destroyed. Okay, so whatever variables that you make inside your loop, don't consider those. Okay, and that's it. There were only 3 variables here, so the space complexity will be O(n). Okay, this is a good example. Now this code is actually in JavaScript, but it doesn't matter. You don't have to understand the code. Just wanted to point a few things. And that is it. That is it for this complete lecture. I hope you understood everything. If you did not, then just let me know in the comments or whatever. If you don't want to comment, then just use the email and mail me. Thank you.